cerebrum, we would have like the midbrain, we'd have the brain stem, right? So the brain consists of different areas. Oh, cerebellum. And when we think about the cerebrum, it sort of is going to have a couple of different parts to it. It'll have this outer part, which is the cortex, and it'll have this inner part, which is tracts. So do you guys know what I'm throwing down, picking up what I'm throwing down there right now, just to get a general idea of what's going on here, right? So the cortex is gray matter, right? And the tracts is white matter. But in the cerebrum, we have even deeper, more gray matter. And that's called the basal nuclei. Are you guys familiar with that structure? Yeah? So then deep gray matter is basal nuclei. Because when we think of gray matter, we're thinking of that being non-myelinated neurons, right? And predominantly cell bodies of neurons. You guys remember that? So then when we think of gray matter here, again, nuclei. Nuclei is referring to the cell bodies of a neuron. So if we think about a neuron, just draw it up here, just a simple picture of it, we're going to have the cell body. And then what are all these things I have here? What is that referring to? Dendrites. Dendrites, yes. And then this part here is
Axon.
the axon. And then this here is, these parts here are the axon terminal. Okay? Are we good with that? This is also. So when we're talking about Parkinson, we're going to have, I want to say that it's, oh yeah, we also have the diencephalon. That's another part. I'm going to say this substantia nigra is in the midbrain. You don't need to know exactly where the substantia nigra is. I'm pretty sure it's in the midbrain. And this is given this name nigra because these neurons that originate here are going to be making melanin. Okay? So melanin is what gives you the pigment of your skin. And so since these neurons are making a bunch of melanin, that area of the substantia nigra is going to be blackish looking or dark brown for that reason. Everybody good with that? And so what happens is we're going to have, I'm going to draw this a little different, just to get a picture to show you what's really going on here. So here is a neuron, okay? Now, you're going to have a collection of cell bodies making up the substantia nigra. And in these cell bodies, I don't have brown, which is a bummer, but I'll use this black. We're going to represent melanin as this little dot here, okay? So here you're getting these neurons that originate in the substantia nigra making a bunch of melanin, okay? Now this melanin is going to be converted into, first of all, it's going to travel within the axon. This is going to do what's called anterograde movement. It's going towards the axon terminals, but it's going to get changed into dopamine. All right? And so the melanin will be made in neurons that originate in the substantia nigra. It has a bunch of cell bodies. They're going to make melanin, and then this melanin becomes converted to dopamine, which is a neurotransmitter, okay? And dopamine will be at the axon terminals of this neuron that originated in the substantia nigra. And they're going to go and synapse with the cell bodies that make up this basal nuclei. All right? So now what I have in green is representing the basal nuclei. Everybody still good? And so this dopamine, what it does when it's released in this basal nuclei normally is makes it so that these interneurons of the basal nuclei are able to control smooth movements, okay? So the basal nuclei has the same function as the cerebellum, coordination of skeletal muscle movement, all right? Being able to actually coordinate your skeletal muscle movement so that you can step and walk in a coordinated fashion, all right? Parkinson, they are shaky, they jolt, they have these jerks. Their coordinated skeletal muscle movement is compromised. And the reason is because these neurons here in the substantia nigra die. And as they die, that means that less dopamine is being released here. And now the basal nuclei is not able to control those skilled motor movements, causing that shakiness and jerkiness that you see, or having a change in their gait, shuffling, because they can't coordinate their muscles to actually walk properly. Okay, all those different manifestations you see in Parkinson's is because this basal nuclei is not communicating with neurons that originated in the substantia nigra because they've died. Everybody good with that one? So what does that make the answer then? What's the correct answer for question 7? What is the correct statement for the mechanism of Parkinson? A. Okay, the B is what happens normally. Okay, so B was normal function. A, the melanin's not being made, and the reason why is because these neurons have died. And actually, Parkinson's patients don't start to show the symptoms until about 70 to 80% of these neurons have been damaged. So it takes a significant amount, but by that time they have been damaged, unfortunately. They can't give as treatment dopamine because dopamine doesn't cross the blood-brain barrier, but one treatment that they're trying with Parkinson patients is the precursor to melanin itself, which is also a precursor to dopamine, to try to help with Parkinson's. Any questions about that? Did that answer your question? Okay, cool. Other questions? I'll go Marisol, because she had her hand up, and then Natasha next.
15?
15?
Yes.
We're looking at 15 now. Okay, so in regards to autoimmune disorders, there's really two big ones here. Multiple sclerosis could potentially be an autoimmune, and this thing called Guillain-Barré syndrome. So the answer there is Guillain-Barré. Yeah, and in both multiple sclerosis and the Guillain-Barré, you get scarring of the myelin sheath. So it's interesting that these two that are autoimmune are going to also have similar pathogenesis. They're both going to involve demyelination of the axon. Okay. Are we familiar with what I'm saying with demyelination? Do you know what I'm talking about with there? Okay. So if I'm going to go, I'll erase this. I can erase this?
Yeah.
Cool. Kill it. Oh, that's
Okay, so,
I think I'll do that.
so both multiple sclerosis and this Guillain-Barré, or Barr, however you say it, okay, they're both going to be considered potentially an autoimmune disorder. But interestingly enough, both of them are having demyelination of that myelin sheath that is over an axon, okay? So if we're thinking about, here is my neuron. Right? These are the dendrites again. Here's the cell body. Down here is this axon terminal. And you're going to also have, depending upon if we're talking about the peripheral nervous system or the central nervous system, we have cells that are going to wrap around this axon. And as they wrap around the axon, they're going to actually insulate. But we call that, whenever they do wrap around the axon, myelination, all right? So if we have like single cells doing this myelination, are we talking about the peripheral nervous system or the central nervous system?
Peripheral.
Yes, because if we're talking about PNS myelination, that means you're going to have multiple Schwann cells myelinating. If we were talking about the central nervous system, then you would have oligodendrocytes. And the way that oligodendrocytes work, rather than having this, you'll have this big, huge oligodendrocyte that'll come down and it'll myelinate multiple interneurons. And actually, the interneurons themselves will have more than just one of these oligodendrocytes doing that, but an oligodendrocyte will myelinate several interneurons, where in this case, a Schwann cell is only associated with one motor or sensory neuron. So pretty good with that? Yeah.
On this one, with the spinal cord, that it has the T cells and the B cells mediating the destruction, and that's the same thing as muscular sclerosis, but
Right.
just ones with the synapse and ones with the axon.
That's very good. We're talking right now about how multiple sclerosis and this Guillain-Barré are both autoimmune,
Oh.
okay? I don't know how to spell the Guillain-Barré. Oh, maybe it's on this little thing. I can see it here. Which one are we doing, 15? Oh, yeah, here it is. Okay, both of these are autoimmune, but Guillain-Barré is happening in the PNS. Multiple sclerosis is happening in the central nervous system. Okay? And so what's happening in either of these situations is this myelination is being attacked. Okay? So you're having autoimmune cell or immune cells come and destroy this myelination. Okay? It's destroyed. So it comes in and destroys Schwann cells, attacks them. For this one. Here, for multiple sclerosis, it destroys oligodendrocytes. Okay, which are the cells that myelinate interneurons. All right? So multiple sclerosis, you get demyelination. I don't know how to spell demyelination. Demyelination of interneurons. All right? And then with this guy, you get demyelination. Oops, I don't know how to spell this. Sorry. Demyelination of motor neurons of PNS, the peripheral nervous system. Okay? Now, with this one here, okay, the progression of this is, you know, this isn't like a chronic thing. Most of the people that have this have spontaneous recovery. They'll first get paralysis of their legs, then they'll get paralysis of their arms, and then they'll get paralysis of their face with this, okay? And then spontaneously, they get movement back in their face. They get movement back in their arms. They get movement back in their legs, and they're fine, all right? Multiple sclerosis is not that way. And this particular one, it varies from person to person in regards to the manifestations that are seen. Okay? Some people have a hard time thinking. It just depends upon where this demyelination is occurring in that central nervous system. So they might have a hard time thinking. Some have a hard time contracting certain muscle groups. So there's a big range. The thing that makes a person have MS, though, is the fact that there is scarring of these interneurons. Now, in regards to what that does, what does myelination do? What's the whole point of it? What?
It helps with conduction.
It helps with the conduction. It helps make that impulse faster. All right? So and the way it does it with this insulation is it makes it to where it jumps over, right? So instead of just having like if this right here is an axon, and we're having action potential along it with a non-myelinated axon, it would go like this, right? And then at the end of the axon, that's going to trigger the axon terminal to release neurotransmitters. So that neuron can talk to another neuron, right? But whenever you have myelination, it does that saltatory skipping thing. So instead, it goes like this. It's faster. And so what happens when these get destroyed, they're replaced with connective tissue. That's the scarring, all right? So these get destroyed, and you're going to have now collagen fibers. Oh yeah, sure, it insulates it even more, but now it can't jump from node to node, and this person cannot have an impulse down this, which means that then this neuron can't talk to another neuron, because you need to have that impulse go down for the release of neurotransmitters at this axon terminal, so that you can have that synapse for it to talk to another neuron, all right? Or to excite a muscle fiber, for example, if we're talking about a motor neuron. Is everybody good with that? All right, Natasha.
Number 20, during repair from a spinal cord injury.
Okay. So for 20, first of all, do neutrophils, are they going to not promote further damage in the repair? No, remember that whole thing, especially like with reperfusion or with any type of, hey, inflammation we're trying to repair, the initial inflammation and those neutrophils coming to that site of injury actually causes further damage initially. So this is wrong because of that. It's going to actually promote further damage initially. So A is wrong. In regards to spinal cord injury, we're just talking about injured cells here. And so we're not really talking about any type of foreign body, unless, of course, we get infected, but let's say we don't. So B cells aren't going to be a major factor here, all right? Eosinophils won't be a factor. Those are very few and rare in our system, and they tend to have the biggest functional role in our digestive tract because they predominantly kill parasitic worms. That's their big function, and so they're killing any kind of parasitic worms we ingested. So that one's out. So that leaves macrophages that are going to promote inflammation and promote further damage.
That's what I got, but I was just...
Yeah, and actually, in regards to spinal cord injury and repair, the big players are going to be macrophages and neutrophils. They're going to play the biggest role here in trying to repair that damage. Other questions?
So the answer was that they promote inflammation?
Yes, it's C. C is the answer.
Number 17.
Okay. So number 17 is talking about this thing called spina bifida. Spina bifida is a congenital disorder. And so, and what spina bifida is is, it's the inability to close the vertebral column, or the vertebral cavity. And so, you know, you got this vertebra, right? We probably should do this. This isn't very good. Trying to think how to, my brain to picture it. Anyways, you're gonna have your spinal cord surrounded by these vertebrae, right? All the way down here, whatever. And so, whenever the vertebral cavity can't be closed, means you kind of have the vertebra now exposed to the outside of it. And there's several different ways that, or several different varying degrees of this inability to close this vertebral body cavity, okay? One is gonna be this, what's called a occulta. And occulta means there's no protrusion of the stuff that's within that vertebral body cavity. So here, it's just open, okay? It's open and not closed. And so this one is no protrusion. And you might suspect when a baby is born, and this is all dependent upon the condition of the mom. Most of this, hey, was she not able to get enough oxygen to the baby? Did she have some type of trauma? Was she on drugs? Was she drinking alcohol? Stuff like that. This has no protrusion here, occulta. But then you have this cystica. And this, it's a cyst now. This one here, they can potentially have an idea that this is happening, even though there's no protrusion, because there's excess hair on back of where it hasn't closed. I don't know why it does that.
Probably the body's way of trying to protect it.
Oh, yeah, maybe so. That's a great answer. Good job. I like it. Yeah, totally, because it's open now, For this cystica, there is protrusion. It's a cyst, okay? And so now, in this situation, you have this, spinal column or whatever. Yeah, this is a crappy picture, but I'm hoping that you still get it. And now you have an actual bulge, and this bulge will be seen on the child. It's like on their back, they will have a big cyst, this big protrusion on their back and spina bifida. And there's two types. You could have, and one is more severe than the other. So you got this bulge, this cyst that can be visible on the back. Now there's one that just has cerebral spinal fluid. That's all that's leaking into this cyst because the vertebral cavity hasn't closed properly. And so in this situation, you actually have this development of this cyst, and within that cyst is cerebral spinal fluid. The other one is going to have cerebral spinal fluid, meninges, and spinal cord within the cyst. So part of the spinal cord, the meninges will be within that cyst now, okay? Now, the one that's just the cerebral spinal fluid is this, think of it as being the smaller one. So it's the smaller word, okay? That's meningocyl. The one that is a bigger problem, has more stuff, is the bigger word. So that's meningomyocele. And so those are the two specific types of spina bifida cystica. So the question is asking, which one involves the spinal cord? C is the answer. Any other questions? Yes.
Number 11, I wasn't sure about that one.
Okay. I can erase this. Okay, for me to talk about number 11, I want to talk about cerebral palsy now. So far we've talked about Parkinson, right? We've talked about spina bifida. We've talked about multiple sclerosis. And we've talked about this thing I can't spell. How do I spell it?
GUI,
G-U-I-L-L-I-A-N
IAN dash EARR.
E.
I think so.
Those are the ones we've talked about so far, correct? Now we're going to talk about cerebral palsy. Put that on our list. Cerebral palsy is also congenital. It deals with the condition of the mom. Again, you know, any kind of trauma while that baby's developing can lead to cerebral palsy as well. But we're talking about cerebral palsy. We're talking, this is one where it's going to deal with motor function. It manifests as an inability with motor function, and so the motor function could be spastic, it could be dyskinetic. What?
didn't get it.
Sorry, what did it say?
She said she didn't quite get that.
Oh, well, hey, we're going over it now. Or ataxia. All right? So those are the three types of cerebral palsy, how it can manifest. All right? Now, when we're talking about spastic, this is due to hypertonia, which is getting to your question. All right? Hypertonia is going to make it to where you have contraction, but it's gonna also ultimately, so think of it this way, hypertonia, that means that those muscles are easily excitable, and so you have contraction. I don't know if you've ever seen cerebral palsy patients, but a lot of them have this hyperflexion going on. And so they hyperflex different areas of their body, but then that's all they do. They can't move that body part. So this actually ends up being paralysis in that area. And so hypertonia is where you're having excess contraction that leads to paralysis, okay? And so this particular type of cerebral palsy, the individual will like either have half of their body is not able to move properly, and it has these excessive contractions. So hemiplegia, which results in paralysis of half the body, quadriplegia, all of the limbs are involved. So any of those plasias where you have paralysis are due in part, are associated with spastic. Is everybody okay with that? Now, when we're talking about dyskinetic cerebral palsy, what's going on here is you're going to have abnormal functioning of that basal nuclei again. Which one of those up there involve the basal nuclei as well?
Parkinson's?
Parkinson, okay? But that was because those cells of the basal nuclei were not getting synapse with the ones from the substantia nigra, right? Dopamine wasn't being released to them. So this one is abnormal functioning of the basal nuclei itself. And the basal nuclei is involved with intentional movements, okay? So and fine skilled motor movements. So for example, so intentional and fine skilled. Well, that's really actually the extrapyramidal pathway. Don't worry about that. I don't want to go into that. Fine skilled motor movements are being affected. And so in this situation, so think of it this way, like if I was gonna go and here's this table and I just do it like this to touch it, that's just a broad, gross movement. A fine skilled movement would be me wanting to, on this flyer here, point to one of these red blood cells and going like this. These people with cerebral palsy cannot do that. They cannot do these fine skilled articulated movements when they have dyskinetic, which is going to be abnormal functioning of this basal nuclei.
It's like writing with a pen.
Yeah, they would not be able to write with a pen. Exactly. They wouldn't be able to do that type of movement or typing, stuff like that. Now, these are very similar, okay? This also is going to be uncoordinated muscle movement is affected, but when we're talking about ataxia, we're really talking about, I mean, this is it in general, uncoordinated muscle movement, but in the case of cerebral palsy, this uncoordinated muscle movement is reflected in gait and posture. And so if you no, if you've ever seen any cerebral palsy patients, they tend to be hunched over and like this. Okay, a lot of them actually are not able to move their legs, but if they were, they wouldn't be able to do it very well. So cerebral palsy and Parkinson have a lot of similarities here, actually. Okay? But with this one, they tend to also have paralysis. Like they can't move at all. And so they, a lot of times the spastic is involved. But you can have a combination of these. It could be just this, it could be that. It just depends upon where the damage is in the brain. So for the question, what was that, 11, 17? 11? What is the answer?
Muscle atrophy at the end of it, even though you do the
Hypertonia leads to contraction.
So, but even when you can't move it anymore, doesn't it atrophy at some, or does it hypertrophy?
They're kind of like this, so it's almost like they're continuously in this contracted state, so like hyperflexion here.
Right.
But they can't move. So the paralysis is from this contraction because they can't do an opposing movement. So the answer is muscle contraction, A, but it's because they're doing this and then they can't. The paralysis is more of lack of movement because they're stuck in this position. Others?
So then
Yes.
for ataxia, the very next question is, would be a lack of, difficulty in purposeful movements or lack of organized motor control?
This one is more purposeful movement, sorry, this intentional, that's what I mean by intentional.
Okay.
So that's the dyskinetic one, where the ataxia is, in general, it's called uncoordinated muscle movement, but in the case of cerebral palsy, we're really talking about how it affects the gait and posture in this one.
So just lack of organized motor control would be the better answer?
Yes, definitely, and cerebral palsy, in general, you're having the motor cortex be affected. Motor cortex is definitely overall being compromised in cerebral palsy in general.
So for number 9,
Uh-huh.
it's not A, basal nuclei, it's motor cortex.
In general, the answer would be motor cortex for cerebral palsy. And in regards to this particular one, the basal nuclei. And so when I put up the answers here, I'm gonna have motor cortex be the correct answer, but I'm gonna say basal nuclei for dyskinetic cerebral palsy. Because the motor cortex is being affected in all of these, okay? So the best answer, if I'm getting you correct with what number 9 is.
Yes.
I don't know what number 9 is.
Where's the damage?
Oh, yeah. Motor cortex. In all of these, the motor cortex is damaged. But, and we're talking about this dyskinetic one, basal nuclei is also damaged. Okay? Let me talk more about this really quick with this motor cortex. So, if we're talking about the brain, we got this brain, right? It's all wrinkly for us. And we got this cerebellum down here. And then we have this central sulcus, this depression in brain tissue here in the middle, right? And then we have this hump, this like bump, you know, we got this, oh, here's a bump, because our brains are wrinkly, right? And these bumps are called gyrus, correct? And so before this central sulcus is what's called the precentral gyrus. And that area here is the motor cortex, right? You guys remember that? You guys remember that? Okay, cool. So, a lot of these disorders we're talking about, or some of them, we're talking about something happening to send signals or messages for proper motor control, right? And you're gonna have these, what are called, they're called upper motor neurons, which I think is a misnomer because they're actually interneurons. They're fully within the central nervous system, right? And they're gonna go from this motor cortex, they're gonna cross over to the other side of the body because we have contralateralization here. But then they're gonna come down and they're gonna synapse with a lower motor neuron. All right? So this here, this cell body that's in that gray matter of the precentral gyrus, which is the motor cortex, this is an upper motor neuron. And cerebral palsy, they have damage to these in some way, shape, or fashion, no matter what, okay? But you could have it be expressed in several different ways depending upon where the damage is and if it involves the basal nuclei, okay? But you will have damage to these upper motor neurons for cerebral palsy. Okay? That upper motor neuron in the spinal cord, in the ventral horn, that, you know how the spinal cord has these horns? Do you remember this picture? You guys remember that picture? So this is that gray matter of the spinal cord, and yeah, it has all this white matter around it. But that upper motor neuron is going to talk to a lower motor neuron. In that ventral horn, that gray matter of the spinal cord, right? But for people with cerebral palsy, these are damaged and so they can't talk. And that's where you definitely have atrophy occurring and paralysis occurring in that situation, for sure, okay? And so in that situation, that means that those muscles are not getting excited because this lower motor neuron doesn't get the message. And so the skeletal muscle that's part of this motor unit doesn't get excited and doesn't contract. So that's what's, like, if we look at the big picture in regards to paralysis of cerebral palsy, that's what's happening here. These guys aren't even getting excited. All right?
So in ALS, both of that are damaged, like the upper motor neuron and the
Right.
lower motor neuron?
So then if we're talking about amyotrophic lateral sclerosis, which is also called Lou Gehrig's